So, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of particle physics with the course code PHY 452, we are at the lecture number 18 and the topic is relativistic kinematics. As we know that the special theory of relativity plays an important role in every field of physics, it also plays an important role in particle physics. So, in this lecture, we will develop not only the basics of special theory of relativity, but also a new notation that is 4 vectors notation. This new notation is important for the particle physics because when we will deal with the kinematics of the different particles in particle physics, it will be easier to use the 4 vector notation as compared to the simpler usual notation. So, let us start with the special theory of relativity, and as you know that the basics of special theory of relativity starts with inertial frame of reference. Inertial frame of reference is a reference frame where we make the measurements and it has no acceleration. That is, it is either moving with a constant velocity or at rest. But the precise and more accurate definition of inertial frame of reference is that is the Newton's first law is obeyed in the inertial frame of reference. And Newton's first law is that when there is no force acting on the particle or any object, then the acceleration of that object will be 0. That is, if it is in the state of rest, it will remain in the state of rest, or if it is moving with a constant velocity, it will keep on moving with that velocity. But the state of the system will not change. So, precisely we can say that inertial frame of reference is that frame of reference where the Newton's first law is valid. So, two inertial systems move with a constant velocity with respect to each other. This is the consequence of the inertial frame of reference, that if we have two inertial frame of references or inertial systems, then both of them can only move with constant relative velocity. So, their velocity with respect to one another cannot change. So, this is another check to know whether one frame of reference is inertial or not. So, suppose you have two inertial frame of references and one of them is moving with changing relative velocity to another one, it means that this first one is accelerating and this is not inertial frame of reference. So, the inertial frame of references will always be moving with the constant velocity with respect to each other. Next, we go to the situation where an event happens in one frame of reference and observer in the other frame of reference measures it. So, the question arises that what is the relationship between the two measurements? So, precisely if we have the frame of reference S prime, as you can see over here, and some event happens in this frame of reference S prime and it measures it. For example, it measures its position x, this is the position x, so to say, and this is the time as you like. And if this event's position is measured with respect to this frame of reference, with respect to origin, and time is measured, or other coordinates are also measured in S prime, and we have another frame of reference, let's say called S. So, what will be the measurements of this frame of reference of this point? Or you can take the point over here as well as customary and measure its position from here, call it let's say x, and measure its position from here and call it x prime. So, what we want to know that what is the relationship between these two measurements, that is the x prime and x, how they are related. This is the question. Before special theory of relativity, this relationship was given by Galilean and we call them Galilean transformation. And these transformations were easy one, although they were relative, they were not absolute, because you can see that x is different than x prime and it is related to the velocity with which s is moving with respect to s prime, or s prime is moving with respect to s. So, they have the some relative velocity, and assume that z and y and other directions are, for example, in this case, let's say call it y or z directions are there is no motion. But after the special theory of relativity, or in special theory of relativity, Einstein introduced the concept of Lorentz transformations, which means that the positions as well as time will be converted with respect to Lorentz transformations. Before that, it were converted with the help of Galilean transformation. One of the aspects of Galilean transformation was that time was taken absolute. But in Lorentz transformation, time is not absolute and time is also relative. So let's go to the, and this is, you can see this is the velocity with which this is moving, and t is equal to t prime, that is initial time. These two reference frames coincided when x was equal to x prime at 0 position. So after that, S started to move with certain velocity, and therefore its position of measuring some event was different than the one which was at rest. Okay, so now we go to the Lorentz transformations. So say for some event in x, y, z in t measured in S, what is the coordinates when measured in S prime, that is x prime, y prime, z prime, and t prime. In these cases, these are the transformations. So x prime is related to gamma x minus vt, and v is the velocity with which this frame is moving, and then y prime is equal to y, and z prime is equal to z, and t prime is equal to gamma t minus v by c square x. So this is an important point, because in Galilean transformation, t prime is equal to t, this t, which means that time is absolute. But in Lorentz transformation, or in special theory of relativity, time is not absolute and time is changing. So you can see that t prime is equal to is not equal to t, but it is even it involves the position. So the second important point in this Lorentz transformation is that when you change the position x prime, it got contribution from time, and when you change the time, it got contribution from x. Okay, so position and space and time are mixed together. So you would have heard from different sources that in special theory of relativity, the space and time are mixed together. They are interwoven. So this is in this context that you can see that x prime has contribution, the space has contribution from time, and time has contribution from space. So they are mixed, they are not separate. Another point is gamma. This gamma is the Lorentz factor. We call it a Lorentz factor, and you see that it appears in both time and space, and its value, if its value is equal to 1, if gamma is equal to 1, you can see that we recover the usual Galilean transformation. If I put gamma is equal to 1 here and gamma is equal to 1 here, then c square will come here, and then we will recover the usual definitions of the Galilean transformation. Okay, and this is exactly the gamma factor, which is equal to 1 over 1 minus v square by c square. And next is also an important thing is about the inverse transformations. So here you have seen that x prime is related to x, but what about if we can put this x onto the left side and take this x prime to the right side? This is possible, and we call them inverse Lorentz transformation, and you can see that these are the inverse Lorentz transformations. And so both are equally good. So it depends which one you call x and which one you call x prime. It depends upon you, but it's always possible to move from one to another, and it is kind of dictionary between two reference frames. So one can always move from one frame of reference to another frame of reference. And important point, some consequences of these transformations, we will discuss one by one. So for example, the first important consequence is the relativity of simultaneity. What do we mean by the relativity of simultaneity? We mean that if we have two events occur at the same time in S, but at different locations, then they don't occur at same time in S prime. So what do we mean by this relativity of simultaneity is that if I have two events, for example, event 1, call it P1, and an event 2, call it P2. So if these two events are simultaneous, that is they are acting at same time t is equal to 0, for example. So in one frame of reference they will be simultaneous, that is they have occurred at exactly same time. But the other frame of reference, it is possible that this P1 occurs first and this P2 occurs later. So the order is changed. We call it the simultaneity, the relativity of simultaneity. That is, the two events are, the simultaneity of two events is relative, it's not absolute. The order in which these two events are occurring is not independent of the frame of reference. It depends upon the frame of reference. So in one frame of reference it is possible that these two occur at same time. Another frame of reference it is possible that one of them occurs first and the second one occurs later. So this was the first consequence. The second, you can see also from this mathematical relation that t prime a is equal to t prime b, and these are not simultaneous. So when event a and event b are occurring, it is not simultaneous. The second popular example is of length contraction. This is the consequence of the Lorentz transformation, and we know that lengths are shortened for moving objects. Remember, whenever the objects are moving with high speed, that is a speed comparable to the speed of light, then lengths are contracted or they are shortened. And the formula for this is L is equal to L prime over gamma. So this factor gamma is the Lorentz factor, and if it is equal to 1, then both the equations, both the lengths are equal. But if it is not equal to 1, that these lengths are not equal. So we see that the lengths for moving objects, so if we have two frame of references and one of them is moving, so in that measurement from that frame of reference of any object will measure the shorter lengths. And another another consequence is of time dilation. By time dilation we mean that moving clocks runs slow. Again, if we have two frame of references and one of them is moving with a velocity comparable to the velocity of light, please note that these all effects are quite visible at velocity which is comparable to the velocity of light if the objects are moving with that velocity. At lower velocity, these all results reduce to the non-relativistic values, because the effect of relativity is only prominent when the objects are moving with the velocities which are comparable to the velocity of light. So moving clocks run slow in time dilation. So if there are two frame of references, that is S and S prime, and if one of them is moving with a certain velocity comparable to the velocity of light, the clock in that will tick slower. That clock will tick slower, and the time will take longer. That's why we call it the time dilation. And this is the mathematical relation, t is equal to gamma t prime. So you see that it is directly proportional. So this time is greater than this time because it is multiplied with the gamma. So time dilation is also an important consequence of the special theory of relativity. Another one is the velocity addition. In Galilean transformation, it was possible to add velocities simply, and this was one of the contradictions with the physical reality that invoked Lorentz transformation or special theory of relativity. And now in Lorentz transformation or a special theory of relativity, you see the velocity of the object. For example, this u is the velocity of the object in one frame of reference, and u prime is in another frame of reference, and v is the velocity with which the frame is moving. So this is the relation for the addition of velocities. So this is also the consequence of the special theory of relativity or the Lorentz transformation. So as I promised that we will develop the 4-vector formalism. This was only the review of some basics of the special theory of relativity, but now we go towards developing the 4 vectors formalism. So what do we mean by 4 vectors? As you know that in special theory of relativity, time is also a coordinate. So now we have 4 coordinates instead of 3 coordinates. So our vector lives in 4-dimensional space. That is, we have time, and 3 space dimensions x, y, z. So therefore our vector will have 4 components rather than 3 components. It will have 4 components. So in special theory of relativity, and especially in particle physics, we use the 4 vectors notations. So physics will not change. Either you use 3 vector notation and treat time separately, I mean just for the notation's sake, or you use the 4 vector notation. Physics will not change, but it is a compact notation. You will see now it is a compact notation and quite useful, especially in particle physics. So what we see, what we say that there is a first coordinate x naught which is equal to ct. This is time coordinate. So you will be wondering why I am multiplying c with it. The reason is that I cannot say that time is equal to space. I can only say that space is equal to space. So if I want to put time over here, I have to convert it into the space dimensions. That's why c is multiplied over here, and we call it x naught. So x naught is the time coordinate, and it is although it is time coordinate, but dimensionally we have to correct it and multiply with the speed of light, so that it is space in terms of dimensions. But then since time is entering into here, so we call it a time coordinate, and then the 3 usual space coordinates are here, that is x1, y. So another important thing in this notation, you will be noticing that we are putting superscripts over here, or the indices. So this 0 index mean that it is a time dimension, and we call x as x1 and y as x2 and z as x3. So it will not change the physics, but it will give us a compact notation, 4 vector notation. That's why we are changing x to x1, y to x2 and z to x3. Then by this way we will be able to combine them together. Okay, so let's see how we do this. So Lorentz transformation in these 4 vector notations are now, you see, it's just the change of notation. So time is x0 now, prime. So same transformation we treated before, and here we introduce a factor beta as well, and the beta is actually v by c. To shorten the writing, we have put v by c is equal to beta. So this is the then x transformation, this is the y transformation, which is now x2, and this is the z transformation, x3. So you see that in this notation we have first converted Lorentz transformation from usual to this one, and then now we will combine them into one equation. So these are 4 different equations appearing here, but in this 4 vector notation we can just put them into one equation over here like this. So you see this now, x mu prime is equal to, where nu goes from 0 to 3, x mu nu, x nu, where mu and nu both goes from 0, 1, 2, 3. So when you put 0 over here, you get the time component. When you put 1, you get the x component of the space. When you put 2, you get the y component of the space, and when you get 3, put 3, you get the z component of the space. So you seen that in the 4 vector notation, quite easily we have converted 4 equations into one equation with this. Even we will get rid of this sum by the Einstein summation convention, which is also very useful, where we say that whenever some index will be repeated, one in the upper and position and one in the lower position, then the summation will be automatically there. This is called the Einstein summation convention, and we will even get rid of this summation symbol, and whenever this nu is repeated, it means we have to sum over nu over its range. So we don't have to write nu is equal to 0 to 3. So even further simplification. So in particle physics books, you will find out this notation even without this sigma sign, and x mu prime is equal to and these gamma matrices, these lambda matrices, Lorentz, these matrices are actually will be constructed out of these 4 equations, these values. And if you look at them, then lambda 0 0, because when nu is 0 and mu is 0, this will give you lambda 0 0, and this was equal to gamma, if you remember. And if you put lambda 1 1, this was also equal to gamma, because in space, in the time there was a gamma, and in the x there was a gamma, but in y and z there was no gamma. Therefore lambda 2 2 and lambda 3 3 are not equal to gamma but equal to 1. And then the mixed components, that is 0 1 or 1 0, are minus gamma beta, and the rest of them is equal to 0. So by this way, if you not gamma, lambda, so all these values of the matrices, this matrix lambda over here, 0, 0 and 1, 0 are just coming from this set of equations. You can read them from here. So we have just converted this set of equations into this one and then constructed these matrices values. So now you see that it went to very compact notation, this 4 vector, and that's why it's also very useful. And over here you see now we have constructed all these values for lambdas, and you can read off from all Lorentz transformation these matrix values. That's a simple exercise. If you can read off which of them having which values, you can just compare with them and see the rest of them are equal to 0. Okay. So another concept is invariant. What do we mean by invariant? In any relativity theory, although even in Galilean relativity or in special relativity or in any other relativity, we always have some observables or some physical quantities which are invariant when we go from one frame of reference to another frame of reference. For example, if we have S and we have S prime, if we move from S to S prime, there will be some quantities will not change, which will not change. For example, in Galilean relativity, we remember that time was invariant. T and T prime are equal. But in special theory of relativity, time is not invariant, time is not absolute, and position is also not absolute, but combination of them is absolute. That's very important point. So you can see over here that we will construct this invariant from the combination of space and time, that is x0 square minus x1 square, x2 square, x3 square. This is called the interval, the space-time interval. Before that, we were using time interval and space interval separately, but now we are constructing the space interval and time interval. We are combining them and constructing the space-time interval. So the space-time interval is invariant. By invariant, we mean that you can see on here that is x prime and the primes quantities and the unprimed quantities are just equal. So x0 can be different from x0 prime. X0 can be different from x0 prime, x1 can be different from x1 prime, x2 can be different from x2 prime, and x3 can be different from x3 prime. But this whole quantity over here, this one and this one are just equal. We call it an invariant. And there are different invariants, but this is the most important invariant by definition. We call it a space-time interval. So when in special theory of relativity, it can happen that space contracts and time dilates, but combined together for both references, this will remain unchanged. And this space-time interval in compact notation can be written as mu is equal to 0 to 3 going for an x mu and x mu, because you see that it is square, so square is calculated like this. And this is this another matrix called G. This G matrix or metric, we call it a metric. So this metric is also very important. So you see sometimes there are negative signs over here, and it is also a convention to put negative signs in space coordinates, or this is called northeast dimension, northwest dimension. You can also have south dimension, in which you put minus sign over here and plus signs over here. These are two conventions which you can use, but this minus signs are captured over here. So when I will use G mu nu over here, at the moment we have not used here, but we can use this G mu nu, this metric, and this metric is actually capture everything. This is a dynamical property and very important property, and very important quantity in general theory of relativity. Actually, in special theory of relativity, this metric is called Minkowski metric. So this is called Minkowski metric, and it represents the flat space 1 minus 1 minus 1, or you can write minus 1 plus 1 plus 1. Both are equal. Only requirement is that space and time coordinates should enter with the opposite signs. So if you entering the space with negative, then time will be positive, and if you entering time with the negative, then space will be positive. They should have the opposite signs, otherwise this special theory of relativity will not work. It only works for this when the signs are negative, opposite. And here you see that this metric is called Minkowski metric, and it represents the flat space. and when we are on the curved space, then these numbers will be different. You will have different values at different positions. Okay, but at the moment you just remember that this is the metric entering here. And what is the covariant? What we can do now with the help of this metric G mean U, that we can have two types of vector. First note that we can have two types of vectors. This vector over the right side, which has an upper index, and this vector over the left side, which have the lower index. They are two different vectors. They are not the same vectors. This usually we call a covariant vector. One is a contravariant. This we usually call a contravariant vector, and this we call a covariant vector. So contravariant, and a covariant, and usually they are conjugate to each other. Whenever we do the scalar product, we actually are multiplying this contravariant or covariant vectors together. So this G mu nu has another important application, that it can convert a covariant vector or contravariant vector into covariant. You see that this new index is contracted, and we call it a contracted index, and this is a free index. So requirement is that this free index must be the same on both sides of the equation, but contracted index cannot appear or may not appear on the other side. So you can see when G mu nu multiplied with the x nu, this contracted index gone and mu is coming here, but since it's downwards, it's downstairs, so therefore this mu is coming on the left side downstairs, and by this way we have converted the contravariant vector into the covariant vector. So this is one of the tasks which G mu nu can perform. And it also that these x mu, this contravariant or covariant are inverse of each other. It can be inverse of each other, and gives us the identity for any vector. And we can also have another vector. This is the space, because it's very usual to work with this with the space intervals or with the space vector, displacement vectors. These are the displacement vectors. But for general vector, this is also true. So assume that this A mu nu is a general vector. So this is a covariant, contravariant, and this is a covariant, and this metric is converting the contravariant into covariant, and for a general vector. And also the other way around is also possible. So inverse of the G mu nu is this G mu nu, and one can convert the covariant into contravariant. So both are possible. With the inverse of this metric, we can also do this reverse operation. So this is a time to give you an example. An example is that if we want to calculate the interval for a general metric, general vector, this mu nu or mu nu, both are possible. They give you this one, and this is actually invariant under coordinate transformation. And well, this is a very important tool as well to check the invariance of something, that under coordinate transformation is something is invariant. We say that it is a physical object. And from this we get three situations. We see that a square, so this is equal to actually a square. We have calculated a square either by a mu b mu or a mu b mu, both will give us the same thing. And a naught b naught is their splitting them into the space time and time space part and time part. And now you see that there are three possibilities. Either the space part is time part is greater than the space part. In this case, we will see that a square will be positive, or this space part is greater than the time part. So in this first case, you see that a square is positive, definite, and it is only possible that this time part is greater than the space part. We call such events as time-like event, because time part is greater than the space part. We say them are time-like events. But on the other hand, if this one is greater, we will have negative, and we will call them space-like, because now space is greater than this one. And if they are equal, we call them light-like. And why they are called time-like and space-like and light-like, they are practically very important, because the physical objects are always time-like, And space-like are not physical objects because they cannot travel. You cannot travel with with the speed greater than the speed of light. Here the speed is less than the speed of light, and here the speed is so in this case we have v is less than c, and here we have v is greater than c. So they are not physical, these space-like intervals. And when we have v is equal to c, so only light can travel with this speed, and we call it, that's why we call it a light-like. So we have this cone. So cone, here we have space-like, here we have light. So this is space-like region. This is here we are. This is our future, and on this this slanted line is a light-like. This region and this region is a space-like, and this is the time-like. So we live in this cone over here. This is called time cone, and this cone, the space-like events are not reachable, and these slanted lines are only the photons or light can reach to them, and we live over here. This is our past, and this is our future. So with this, we have in today's lecture reviewed the special theory of relativity, the basics of it, and then we have developed the 4-vector notation and discussed some time-like, space-like and light-like events as well, and we have discussed invariants and how to construct invariants, and we have also discussed the contravariant and covariant vectors. With this, I thank you all.